What if you could reprogram Tetris just by playing it? Well, it turns out that you can, and that's exactly what we're going to do. We can write code using name entries and scores in the high score tables. Then we can activate that code by using extra controllers and pressing specific directions on their D-pads at a moment in time when the game would normally crash. In the end, we'll test the experiment on an emulator and then on real hardware. Let's go. Today, players are progressing deeper into the levels of Tetris. They've managed to move past level 150. Unfortunately, as we reach these higher levels, the computation for clearing lines may take so long to complete that the game crashes. We examined the details of a crash in a previous video, and there are many times that it can happen during gameplay throughout these high levels. The crash occurs when this code, an area I called the jump handler, is interrupted during its execution. An interrupt occurs at the end of each frame to signal the CPU that, hey, it's time for the next frame, go do your next frame stuff. The CPU leaves the work it was doing, handles the interrupt, and then returns to where it was. In our crash example, the jump handler was interrupted. Unfortunately, we may return to the jump handler with different values stored in addresses 0 and 1 versus what they were before the interrupt occurred. These addresses are used to determine where the jump handler is going. They were changed inside the interrupt handler logic. This resulted in our jump taking us somewhere that we didn't want to go and crashed the game. What we're going to do is use this misdirect to go somewhere that we want to go, somewhere the code still doesn't intend for us to go, but is yet a place of our own selection thanks to controller input. The community has created a crash theory spreadsheet to detail crash scenarios. This document is amazing. This sheet illustrates the percentage chance you crash the game based on criteria indicated by the various columns. It spans levels 155 to 255 and provides crash percentages for clearing lines that would transition you into the next level, or even simply landing a piece during the highest levels. Let's focus on the transition details for a single line clear from level 154 to 155. If we clear a single on this transition, there's a high probability that we crash. If we know we are clearing with a single, pressing select so that we have no next box is one way to dodge the crash on this transition. But dodging is not what I want to do. I want to meet crash criteria. Not only that, but I want to meet very specific crash criteria for transitioning into level 155 with a single line clear. The jump handler is called multiple times per frame, and the values stored in RAM addresses 0 and 1 are always changing. If we're going to manipulate the values at those addresses, we need to target a specific call we know we can crash and know which line of code is executed just before the interrupt occurs. So let's work toward that. What do these other columns mean? PD stands for push down. Clearing a line isn't the only way you can score points in Tetris. When you press down to accelerate a drop, you get points for it. The manual states the higher the position that the block is dropped from, the higher the score. The dividing line in the spreadsheet is if your drop score is under 7 points or 7 points or higher. Pressing down for a score less than 7 on this single transition into 155 has an 86.67% chance to crash the game. NNB stands for no next box. We just talked about this one. Turning off the next box piece will dodge this particular crash. Finally, we have clear count. This one is the least obvious aspect of crash criteria. Tetris keeps a count of each of the 4 different types of clears: single, double, triple, and Tetris. Those counts are stored in RAM and are not visible to the player. That said, we can illustrate their values easily in an emulator by using a Lua script. With the Tetris AI playing the game for us, you can see the totals rolling up on the left side of the screen as lines are cleared. If the clear stat crosses a multiple of 10, it may have a bearing on if a crash occurs or not. In the case of our targeted crash, it has a very high probability of crashing the game. Finally, if we don't push down for any points, don't hide the next box, and our single line clear doesn't cross a multiple of 10, then we have a 100% chance to crash the game. And this is our target, standard. How do we achieve it? You'll notice that there are different colors behind these crash possibilities. The colors correspond to the lines of code inside the jump handler. Despite the jump handler having certain colors associated with specific lines of code, in reality, where we land is best represented as a spectrum. Instruction execution time is measured in cycles. How many cycles were consumed to execute the current frame's instructions before executing our jump handler has a bearing on when the interrupt occurs. Fewer instructions executed before the jump handler means we can execute most of the jump handler before an interrupt occurs. The more instructions are executed before the jump handler, the earlier the interrupt occurs inside of it. That makes sense. We have a general idea of give and take, but we need to narrow our interrupt down to an exact moment, or at least a very small window of time. Just look at how many references are made to temp 0, temp 1, or both inside the jump handler. When we modify these values for hijacking execution matters. Fortunately, the spreadsheet also contains a calculator that helps us zero in on which lines of code are executed before the interrupt occurs. Pause the video if you would like to read the details. You'll notice that there is more here than just the simple columns we covered earlier. I have specified the criteria in the input section of the calculator, and the results are below. Our odds of crashing are 100%. We are most likely going to interrupt after a line of code in the yellow section, but there is a sliver of a chance that we may interrupt after executing the orange section. Best to account for all possibilities. We've narrowed it down to 4 lines. Interrupting after TAX or I and Y is irrelevant. That leaves interrupting after the single orange line or the yellow line immediately below it. There are 2 locations in time that we will influence by changing temp 0 and temp 1. To review, here is our request list for the player so far. Reach level 154 and set yourself up so that a single clear will take you to level 155. Drop the final piece into place without pressing down, with the next piece shown in the next box, and without crossing a single line clear count that is a multiple of 10. Or for that last part, just cross your fingers. This sets us up for intervention, using additional controllers to somehow change the values at these RAM addresses at this moment in time. And the results of our endeavor? Temporary crash elimination for over 10 levels. How is this possible? Saddle up the horses and grab the tacos, because we're going to find out. We are set up for guaranteed disaster, and there are prerequisites to turn it into a success. Welcome to Displaced Gamers. Controllers play a big part in hijacking this train, so let's talk about them. A previous video on this channel examined NES controller electronics and explained how they work. If you haven't seen the video, I highly recommend it. There are 2 controller ports on the front of the NES. Their pinouts look like this. They can be accessed in code via register 4016 hex and 4017 hex. Code uses latch to tell the controller to capture the current presses and then prepare for reading those presses one at a time. These D labels you see are data lines used for sending controller data. D0 is used for our gamepad. D3 and D4 are used for controllers like the NES Zapper, for example. When we read register 4016 hex, a clock pulse is sent to controller port 1 to signal a connected controller to clock in its first bit of data. Yeah, just 1 bit, a single press. The byte that we read contains the first bit of all data lines for that port. Our gamepad only uses 1 of them. The first D0 bit read from our gamepad contains the press status for the A button. We are responsible for saving that bit somewhere and then reading the controller port register again to clock in the next press. That next press is the status of B. We continue to read and save until we have acquired the status of all 8 possible presses. They arrive in this order. Since there is a lot of redundancy, we perform this logic inside a loop. Let's move to code. Here is the shell for our loop. Index is set to 8 for the 8 presses. There are 2 controllers, so we want to read the D0 bit for both of them each time through the loop. Since we need to save off that lowest D0 bit from our read, we use a pair of instructions to extract it and save it. LSR shifts all the bits from our read to the right and kicks the D0 bit into the carry flag. ROL rotates all the bits inside our save spot to the left and pulls in the D0 bit we kicked out to the carry flag. This is performed for controller port 2 as well. There's the code to read controller bits. But Tetris does a little more than this. Here is the code for Tetris. Tetris has an extra pair of LSR and ROL instructions after each read. That means it kicks out and saves the D1 bit, and I've hidden the save location for the moment. But where is D1? It isn't present on either controller port here. D1 is present on the Famicom expansion port. The original Famicom has its Player 1 and Player 2 controllers hardwired into the back of the console, while the NES has detachable controllers to allow for hooking up the NES Max or Advantage, for example. The Famicom requires an expansion port to allow for alternate controllers to be used versus the ones hardwired to the console. With this in mind, controller read code for various games would naturally want to take both D0 for hardwired controllers and D1 for expansion controllers into account when checking for player input. We can use an adapter to connect NES controllers to a Famicom expansion port and see D1 in action. We'll call these controllers 3 and 4. Let's use this AV Famicom for our real hardware example. I've hooked up controller 1 and 3. This is the 240p test suite. It is homebrew software used for testing various things, including inputs on the console. This screen lets us not only see the D0 inputs from controller 1 connected to the front port, but also the D1 inputs from controller 3 connected to the expansion port. On controller 1, A, B, select Start, up, down, left, and right. And the same input sequence on controller 3. I can press down on controller 1 and press A on controller 3. Tetris takes D0 and D1 into account for each player and then merges each player's inputs from the pairs of sources. When I press these inputs on these two controllers while in the game, Tetris's controller read logic ultimately indicates that player 1 pressed down an A. And before it merges the results of reading the two data lines, it stores the D1 presses in RAM addresses 0 and 1, the same locations used both for obtaining and jumping to a destination address inside the jump handler. The same locations that were responsible for redirecting code execution to RAM and crashing Tetris in the previous video. Wow, these two RAM addresses sure are popular. 2 bytes in RAM, 16 bits. 2 controllers, 16 presses. Where do you want to go today? When I asked where are we going now after the jump handler was interrupted in the previous video, the answer in part is based upon any controller presses read from the D1 lines of the expansion port. The controller read logic is our last pit stop before returning from the interrupt. Both of these bytes are going to be 0 unless controllers are connected and buttons are pressed. The exact moment the jump handler was interrupted has a bearing on where we go. Thanks to our earlier calculator, we know that moment in time. We know when in-game this needs to happen, where in code this needs to happen, and how we are going to make it happen. With all of that in mind, we need to know what values these addresses contain before the interrupt occurs and what new values we're going to assign them using extra controllers. Let's talk about what this jump handler is supposed to do. Each place that calls the jump handler has a bank of possible destinations underneath it in the ROM. A parameter is passed in via the accumulator so the handler knows which address to use for the jump destination. That's what all of this logic does. Take where we came from, find the appropriate destination address using the parameter, and jump to it. The jump handler call that we want to interrupt targets a destination address of 9E27. This is normally the last jump destination in a scoring frame before the interrupt occurs. Eventually, it will be interrupted, and that time has arrived. This is our jump handler interruption and target. Let's set up our code so we can follow the flow of logic. I've added extra space to areas we will influence. The orange interrupt occurs after this line has been executed, and the yellow interrupt after this line. Before getting into orange and yellow interrupt details, let's map the original, normal logic flow without interruption. Starting from the top of the jump handler, our parameter value of 8 is doubled, stored inside Y, and then incremented by 1 for a value of 11 hex. This will serve as an offset below. The base address defined by the values inside temp0 and temp1 is 819F. Base address plus our 11 hex offset gives us our lookup address, 81B0, for the low byte of our destination. The value at that location is 27 hex. Y is then incremented and is 12 hex. Base address plus a 12 hex offset gives us our lookup address, 81B1, for the high byte of our destination. The value at that location is 9E. Our jump destination is therefore 9E27. There is your normal, uninterrupted Happy Days logic flow. Base address is used with 2 offsets to find the consecutive lookup addresses containing the values for our destination. We jump there and logic continues. The top of the screen uses numbers to summarize how we find our jump destination. Now, what about when logic is interrupted? Let's look at the orange interrupt scenario first. Our early logic executes as usual. Then just after this STA temp1 statement has been executed, our NMI occurs to interrupt logic at this moment in time. Our temp0 and temp1 addresses are changed inside the jump handler courtesy of our controllers. Each lookup is affected. So how do we want to influence the orange interrupt logic? Let's work it backward in order to find out what our controller presses should be. RAM address 727 hex is where I want to go. This RAM address is part of name entry in the B-type high score table. I selected the low byte of 27 hex because it is the same low byte used for our original destination. The fewer variables, the better. Now, from what address do we retrieve these values? 719 hex and 71A. These locations are also part of name entry in the B-type high score table. This is important. Both the addresses used to look up our destination and the destination value itself are in the B-type high score table in RAM. This gives the player the ability to define the destination values by simply achieving a proper score and using name entry to enter the values in the proper places. That just leaves the base address needed to get us there, courtesy of controllers 3 and 4 and our jump handler code. And that base address is 708 hex. 7 and 8 are the two values that controller 4 and controller 3 need to place inside our temp1 and temp0 locations. Okay, how do we do that? Back to the 240p test suite. Right is 1, left is 2, down is 4, down plus right is 5, down plus left is 6. We are counting in binary using combinations of presses. Each press equals 1 bit inside a byte. 8 is sent via a simple press of up on controller 3. We can clamp that down and leave it alone. Now remember that anything we press on controller 3 will still be considered an input for player 1. Fortunately, up is not used during gameplay. Pieces can still be moved left and right as well as rotated with the A and B buttons. What about controller 4? The good news is we don't have to worry about this controller affecting gameplay. The bad news is we need to press down, left, and right at the same time to send a value of 7. Due to how the gamepad is designed, pressing left and right together isn't possible. The bottom of the plastic D-pad has a center point for pivoting. This also restricts the ability to press opposing directions. So you'll either need to modify a controller by sanding this thing down, find an old controller where it was worn down naturally, or find an alternative NES controller that lets you press the equivalent of left and right at the same time. In my case, I built my own controller with switches because computer science. Left, down, right. Controller 4 is good to go. There it is. That's how we handle the orange interrupt scenario. Ah, but yellow is the most likely interrupt scenario. What about that one? How is it different? Yellow is a hybrid of original and orange. Watch this. The yellow interrupt scenario occurs after the low byte lookup value has been retrieved at this moment in time. That means low byte retrieval is the same as it was for the original scenario. That's why I kept the same low byte destination value. It doesn't matter if we got it from 81B0 or 719 hex. The value is 27 hex. The second half of location retrieval is just like the orange interrupt scenario. The values from the controllers unite to create a base address of 708 hex, and the offset of 12 hex points us to an address of 71A. High byte destination value is, once again, 07. All bases are covered, no matter when the interrupt occurs. After our orange line of code or after our yellow line of code, we are jumping code execution to address 727 hex. Now, the big question: how do we program the game to do something? Our moment has arrived. You're gonna love this. The high score table occupies a large percentage of the 700 hex block of RAM. Remember that there are two high score tables, one for A-type and one for B-type. The RAM layout looks like this. Each section is contiguous. All the names are together. They are followed by all of the scores and then all of the levels. Note that there appears to be space for 4 high score entries in RAM instead of just the 3 we can see. These fourth slots are filled with zeros. We won't access them. To make changes, we have to play the game and obtain a few high scores for name entry. The slots where we want to place are A type 2 and 3 and B type 1 and 3. Now, the entire span of RAM addresses for the high score table is in the range of 700 hex to 74F. For the code I want to write, I don't need all of these addresses. I'm not going to use the levels for anything, so we don't need that section. We don't need to achieve first place in A type, so our starting address is 6 bytes later. I only need the name entries for the B types, so the specific scores used to reach those slots aren't needed. So we're looking at an area spanning 706 hex to 738 hex. Let's move from a screenshot to an illustration for this span. All RAM addresses are present, and all high score sections are labeled. We know that the phantom fourth slots are filled with zeros, so we can fill those in automatically. As for the values we can change, here's how it works. 727 hex is our target for the jump. This is the starting position for treating values as code. As mentioned, to get us here from the jump handler, we need the addresses 719 hex and 71A to contain 27 and 07 respectively. Both are defined by the first name entry in the B type high score table. So the prerequisite here is to reach the highest score in B type during gameplay and enter a name with a left parent followed by a G in these exact slots. The other characters do not matter. For our RAM table, I will use a small asterisk to represent irrelevant values. Each character available to name entry is represented by a value. A is 1, B is 2, G is 7, left parent is 27 hex. That's how we set our numbers in RAM. That takes care of navigating code execution to the high score table, courtesy of extra controllers and jump handler manipulation. And now, it's time to write some assembly code. And boy, are there some restrictions here. You want bare metal programming? You got it. Instructions are represented using opcodes. Perhaps I want to write code using the instruction LDA. Load a value into the accumulator. Here are several examples of it. Even though each instruction is LDA, they use different opcodes depending on the operand's origin. Load from 0 page in RAM, A5. Load a hard-coded value, A9. We don't have access to all of the instructions. We are forced to use a limited instruction set that is based on if we are programming using name entry or programming using the scores. So instead of just writing the code we want to write, we have to limit our instructions to whatever opcodes are available and make the best of it. All symbols that are entered for a name are represented by a number within the range of 0 to 2B. That's 43 possible symbols, or 43 possible opcodes. Remove the illegal opcodes that have been grayed out in the chart, and we are limited to only 25 instructions when using name entry. The scores, as you know, are maintained in RAM as binary coded decimal. The only valid values are 0 through 9. Therefore, we are restricted to opcodes that do not contain letters. With these restrictions in place, and knowing that to write code using scoring, the player is required to achieve a specific score, what do you do? Seriously. If you're a programmer, pause the video here and solve the challenge. It's a lot of fun, trust me. What would you do? How would you do it? Obviously, you'd need to know the RAM layout for Tetris, where everything is stored and such, and that information is out there on the web. My goal is to zero out the high byte of the current score, address 75 hex, with the intention of alleviating the workload of the line clear scoring logic. This temporarily removes the chances the player will crash the game, as scoring logic no longer pushes us into the danger zone for a crash. The chances of a crash from this point forward are eliminated, so long as the player keeps the score under the maximum. Of course, this will inevitably happen somewhere around level 168 or 169. And this is how we do it. First up is code at our destination, 727 hex. We'll use the last 3 bytes of the name entry for the third slot on the B-type high score list. The code is a jump to subroutine. Name entry doesn't matter for the first 3 characters. The last 3 should be 5, F, and G. The values for these are 20 hex, 6, and 7. This code jumps to the subroutine at address 706 hex, the first character of second place for A-type. Now we have some running room. Whenever you jump to a subroutine, the address you just left is placed on the stack so a return from subroutine statement knows where to go. We do not want to return to that place, so we need to get these values out of here. We don't have access to the opcode PLA to pull values from the stack and place them in the accumulator, but we do have access to PLP. This pulls the top value off the stack and uses it to fill the status flags. That's fine, we don't care what those are right now. 2 bytes to pull, 2 instructions to execute. Characters 1 and 2 in second place for the A-type high score table should both be right parent. The opcodes are both 28 hex. Next up, we need to write a 0 to the player score's high byte. We can't load a 0 into the accumulator for this write. The opcode required is out of range. However, we can execute an AND statement and just AND the accumulator with a value of 0. This still does what we need it to do, turns the accumulator into 0. Characters are quote for the and dash, or no entry, for 0. The associated values are 29 hex and 0, of course. With the 0 in the accumulator, we need to write it to RAM address 75 hex. That is the RAM address where the top third of our score is stored, and it is well out of range of our enterable opcodes via the name entry screen. We need to execute code inside the score area. So, let's branch forward a certain number of bytes to skip over all remaining name entry bytes, Howard's high score of 10,000, and the top third, a single byte, of the second place score of A-type. To do this, we're going to branch if positive to address 734 hex. The characters for this are P followed by right parent. The opcode is 10 hex and the branch distance is 28 hex. Couple of things to explain here. First of all, 0, the value in our accumulator that we are checking, is considered a positive number. Therefore, this check is true. We're gonna branch. Second, the instruction is followed by a single byte as branching is relative. We don't say go to address 734 hex. We say branch forward or backward so many bytes. 28 hex will get us there and is conveniently within the range of values for name entry characters. With the program counter now at address 734 hex, we've reached the steepest requirement. The player must obtain a score of exactly 8,575 to enter the characters mentioned in slot 2 beneath Howard. When interpreted as code, 85 hex is store accumulator, STA. We are storing a value of 0. There are multiple STA instructions in our set, and 85 hex is the one for storing a value at a 0-page address, a single byte address. This is, of course, 75 hex, the place where our top third of our score is stored in RAM. This instruction will drop our score to 9,999 and significantly reduce line clear scoring logic time, albeit temporarily. All that is left to do after this instruction is return to regular game code. To do that, obtain third place on A-type. Name entry does not matter here. The only requirements are that the top third of the score is 0 and the bottom third is 60. The 0 opcode is break. This operation is rather interesting, but the key takeaway is that it advances the program counter forward by 2. That allows us a wildcard value for this middle third of the score, as the CPU will never process it. That makes it pretty easy to place a value of 60 in the low byte. 60 is RTS, return from subroutine. That gets us back to the main game code. Remember, we removed our return address of 729 hex from the stack earlier. That means RTS will use the bytes that were previously underneath 729 hex to know where to take us. Done. Some high scores, some names entered. So long as these values are in place and the crash requirements are met, we will clear the high byte of the score and not crash the game. All of these requirements I just provided are mathematically possible. I played the game and obtained them legitimately. Our setup is complete, but will it work? Let's test on the emulator first. The input setup console type is set to Famicom and includes a 4-player adapter connected to the expansion port. Standard controllers are assigned to player 3 and player 4. We'll start an A-type game and let the Tetris AI play its way up past level 150. While it does that, we can use the input button setup area of the debugger to simulate holding up on controller 3 and left, down, and right on controller 4. With the action slowed down on the doorstep of level 155, we see the line clear occur and the game doesn't crash. Our code was successful. Once the first piece lands during level 155, the score graphics are updated to reflect our change. Bingo. The first line clear on level 155 will update our percentage of frame time for scoring cycles inside our overlay. Wow, what a drop. If we let the AI continue, the maximum score isn't reached again until around level 169. Unfortunately, this means the Crash Theory spreadsheet comes back into play, and this level is in the heart of Crashville. You're on your own from here. Perhaps the same redirect could be triggered at a later time, or perhaps the initial crash target criteria should be elsewhere in general. This video is just an example of what could be done, but the real fun for this video is testing on real hardware. Technically, this requires a highly skilled Tetris player, and technically, modifying the game code in any way means I'm not playing on an original unmodified game cartridge. That said, I'm going to employ a few Game Genie codes. Call it programmer prerogative. One slows down the drop speed because, yeah, I can't play at high level speeds. Another pair of codes converts the piece's delt counters so the number of single line clears is present in the area that normally counts T pieces. That will help monitor the clear count crash criteria. With up clamped on controller 3 and the controller 4 switches turned on for left, down, and right, the moment of truth has arrived. Got it. And score graphics are now updated. Whew. I hope you enjoyed this rather unorthodox approach to Tetris analysis. Please like and subscribe if you want more behind the code videos. I also have a Patreon that really helps me out if you are interested. Leave a comment with what code you would write using the high score table of Tetris, and thanks for watching.